I've got a couple, I think, well, relatively tough examples for you. They're not too bad. A box of gravel with a mass of 130 kilograms slides on a rough surface. We've seen that very recently. Being pulled by a bucket of concrete, mass 65 kilograms. Oh, okay, suddenly this is looking a whole lot more like an Atwood machine. We need to find the speed of the box of gravel after it has moved 2 meters. The system starts at rest. I have redrawn the setup for you here. 130 kilogram mass 1, 65 kilogram mass 2. Mu was 0.4 according to the slide, and we need to find the velocity after m2 has fallen by 2 meters. The initial velocity was 0 meters per second. Now I say we need to find the velocity after m2 has fallen 2 meters. If m2 has fallen 2 meters, how much has m1 moved? Oh, also 2 meters. They're connected by a rope. That rope is not going to increase or decrease its length as either of these move. The rope should stay however long that it is, and so as this thing moves, that thing will have to move by the exact same amount. And if this thing is moving at 1.8 meters per second, I don't know, making up a number, then this one also has to be moving at 1.8 meters per second. They have to be moving at the same speed because they're tied together like that. That does simplify things. We're not looking for the particular final velocity of either one, we're looking for the final velocity of both. But if we find the final velocity of one, then we have found the final velocity of the other. We start, as we always do on questions like this, with delta E is equal to other work. How I'm going to break this up this time is different than how I've broken things up before, because for the first time, we have 2 objects that we're dealing with. So I'm going to say that the total change in energy of the whole system is the change in energy of object 1 plus the change in energy of object 2. Total change of energy is going to be the change of energy of each of the objects, and that will be equal to the work due to friction. And then you can see these equations start getting very lengthy and messy. The change in kinetic energy of block 1 plus the change in gravitational potential energy of block 1. This right here is change in energy of block 1. The change of energy of block 1 is the change in kinetic energy of block 1 plus the change in potential gravitational energy of block 1. That's that. But look at block 1. It's just going to slide this way. It's not going to fall over. And so the change in gravitational potential of block 1 will be 0 because it's going to stay at the same height. If you have an object staying at the same height, then its gravitational potential energy stays the same as it moves back and forth. And if its gravitational potential energy stays the same, then its change is nothing. And so I can just cross that out. I can say that delta UG1 is nothing, is 0. Then I look at delta E2, and I say, well, delta E2, the change in energy of the second block is going to be the change of that second block's kinetic energy plus the change of that second block's gravitational potential energy there. And that's all equal to the work due to friction. I know that the change in height of the second block is -2 meters. It's going to fall by 2 meters. And so delta Y, change in Y for that is going to be -2 meters. That's where that 2 meters comes in. It's fallen 2 meters. And now it looks awful again because I took delta KE1 and I broke it up into KE1 final minus KE1 initial. Remember, delta is final minus initial, so delta KE1 is going to be final KE1 minus initial KE1. I have that there. But my initial kinetic energy of block 1 was nothing. And so I've crossed it out because the system starts at rest. I said in the problem, this system starts at rest, so the initial kinetic energy is 0. So cross that out. Plus kinetic energy 2 final. Well, okay, yeah, that happens because this bucket is still going to be falling down at the end, minus KE2 initial. Well, for the same reason as this one, the initial kinetic energy of block 2 had to be 0. And so I cross it out. And then I've got UG2 final, the final gravitational potential energy of block 2 minus the initial gravitational potential energy of block 2. I've crossed this one out because, let me show you here, I've set the initial height to be 0 and the final height to be -2. That's what this is saying, that the change in height is -2. And the way that I've implemented that is by saying that it's originally 0 and at the end it's -2. And that's equal to the work due to friction. I can then plug in my equations. Kinetic energy 1 final, well, that's 1/2 m1 v1 final squared. Notice again, we're getting all these subscripts in there. It's mass 1 and it's velocity 1 final. However, I'm going to show you this right now. Velocity 1 final is equal to velocity 2 final. The 1 and the 2 on the velocities, that doesn't really matter. It's just the final velocity. But anyway, we do that for block 1. We do it again for block 2 final. And we do this for change in gravitational potential energy final for block 2. Notice how many words that I'm saying every time I have to say some of these things. This is the final gravitational potential energy of block 2. That's so many words, but if you take it one word at a time, okay, it's the final at the end of the problem. Gravitational potential energy, okay, it's the energy, the potential to do something because it's falling. Gravitational potential energy, final at the end of the problem of block 2, because we're looking at this thing. It's, I guess, bucket number 2. And it went down by 2 meters, so -2. And still all equal to work due to friction. The work due to friction here is going to be the force times the displacement times the cosine of theta. That's always true. The work is force, displacement, cosine theta. The force of friction is mu times n, as we already know. The displacement is going to be 2 meters because this friction is not happening on block 2. It's happening on block 1. Block 2 is experiencing no friction at all because it's not touching anything. Only block 1 is experiencing friction, and it moves 2 meters that way. Friction is pointing on it this way, but it's moving this way. And because of that, the cosine is 180. And cosine of 180 is -1. So the work due to friction is mu, well, that was 0.4 according to the problem. That's the coefficient of friction, or how strong friction is related to the weight of something, times the normal force, which is going to be mg, because there's nothing weird going on pushing this up or down. Remember, if you have something pushing down on it or pulling up on it, then the normal is not going to equal mg. And you have to solve what the normal is based on it not like falling through the surface or leaping off the surface. That times 2 meters times -1, that's going to be the work due to friction. And so I can start plugging in all the numbers, and okay, yeah, there's a whole ton of numbers right here. But I've got 1/2 times 130 times v final squared, which we're looking for, plus 1/2 times 65 times v final squared, plus 65, that's the mass of block 2, because that's the thing that's falling down, times 9.8, the acceleration due to gravity, times -2, the amount that has fallen, the change in height, is equal to exactly what we set up here for the work due to friction. And then we only have one unknown in 2 different places. We go back to our algebra skills and we calculate the final velocity is 1.62 meters per second. This is another tough one. Can we cancel out mass in this one? It sure looks like we should be able to, because we've got a mass here in friction, we've got a mass there. In gravity, we've got another mass there. In kinetic, we've got another mass there. In that kinetic, but it's different masses. It's M1 and M2. Because it's different masses, we would have to choose, do we divide by M1 or do we divide by M2? We can't divide by both. Well, we could, but then we would just mix everything up weirdly. You have to divide everything by M1 or M2. And if you divided everything by M1, you'd get rid of M1 there, but then you'd have M2 over M1 and M2 over M1 there and there. So you can't, you have to be very careful with that, with dividing through by mass like that. But often you can, but not always. Another question, are we going to have something that looks like this on the test? It looks rather long and it would take a long time to solve. You are very correct. It would take a long time to solve. What I could do is give you part of a question like this. I could say, for example, I could say, here's your question, figure out how much work is, or how much energy is lost to friction. That could be a question that I ask here that does not require you to do everything. Just how much energy is lost to friction. That's just this right there, that the work due to friction is that. And that could be a problem, that it looks a lot like this, but I just ask about one very particular thing instead. You are correct. I'm not going to give you a problem that's this long and then have just like one answer, but I could do something like give you this problem, but break it up into like 3 different problems, and then what I would do is I'd give you this for the first problem and ask you to find something. And then for the second problem, I would actually change the numbers around and then tell you the answer to the previous one with the new numbers. Like, I might give you this and ask you for what's the work due to friction. And I don't know what number that is, but some number. And then on the next problem, I could say, okay, now that's 110 kilograms and that's 75 kilograms instead. And if you had those numbers, then the work due to friction would be such and such. Now find this other thing instead. And so I would give you the equivalent to the answer to the previous problem, but then ask you to solve it with new numbers. And so you would not be penalized for getting the previous question wrong, but it would be broken up into many smaller steps instead of one giant thing like this. Got one more review kind of question for you that we're going to go over it in partial detail. We're not going to go over every part of it. We've got this roller coaster here. Starts at A, then goes to C, then goes to D, then goes to E, then goes to B. I don't know why they ordered it with those letters. That doesn't make much sense, but whatever. I didn't make this diagram. You start at 2 meters per second up here. You can put the locations in order of lowest speed to highest speed on this roller coaster, assuming that there's no friction. We'll assume here that there's no friction. You can put everything in order, lowest speed to highest speed. You know that as you go down a roller coaster, you speed up. And as your roller coaster cart goes back up, you slow down. And so in energy, you know that as you're falling down, you're giving up your gravitational potential and you're exchanging it for kinetic energy. And so the lowest points on here should be the fastest speed, and the highest points on here should be the slowest speed. If you just put everything in order of the height, that's the reverse order of the speed. So if you're wanting to get from the slowest speed to the highest speed, you'd say, well, A is going to be the slowest, 2 meters per second. D is going to be the next slowest at whatever it is, I don't know. Then B, then C, then E. We're told that we start off at 0 meters per second up here. And so I give you that answer right there. We need to find the speed at each point, and I'll show you a brief example of that. And then we also need to find the normal force acting on point B. When you're at the top of the loop, what is the normal force from the track acting on the cart at point B? We need to find the speed at point D. We're just going to do the point D thing. That's the, that was the top. I didn't actually draw it again, but that was the part where it went like, I don't have, oh, here it is. Like that. So that was A, and that point was D right there. And that was 16 meters, and this was 25 meters right there. And we're going to ignore the rest of it because we're just going to find the speed at point D, and then you can follow along with the math that we're going to do. You can follow that along and make it for any of the other points that we've got. So Y initial was 25 meters. I'm going to set down there to be Y equals 0. And so the initial is 25, the final is 16, and I don't care what happens in between. You know, this roller coaster cart could go like this. It could go like this. It could go like this. It could go like this. As long as it doesn't do something weird and go like up really far, because then the cart wouldn't be able to make it over the hill. As long as it's still just going down, then it can look like whatever it wants to, and it should be going the same speed in any of these tracks, in this track, in this track, in this track, in this track, or in this track. It should be going the same speed at that point. No, if it was going at 2 meters per second there, it should always be going at some particular speed there, no matter what the track is shaped like. That is interesting. Let's see what we can do with that. Delta E is equal to work other. Well, there's no outside work because there's no friction in this case and no one's pushing on it. So delta E is equal to 0. Energy initial is equal to energy final. I just took delta E, made it final minus initial, and then did algebra to move things around. Kinetic energy initial is equal to gravitational potential energy initial. This is just saying, well, my initial energy is made up of these two different things. We haven't talked about springs yet. We will tomorrow. And so energy is kinetic energy plus gravitational potential, and we're looking at the initial. So I is equal to energy final, same thing, kinetic energy final plus gravitational potential energy final. I plug in all those things, all those, you know, kinetic energy initial is 1/2 mv initial squared. Gravitational potential energy initial is mgy initial, et cetera, et cetera. Then I can look, m. I can factor out the m's everywhere. I can factor m out of this. I can factor m out of that. And I can divide both sides by m. Get rid of m so that the mass of the cart never mattered. And then plug in v initial. That was 2 meters per second, according to the problem. Y initial was 25. V final is what we're looking for. Y final was 16. Plug all that in, and I get 13.4 meters at point D, right there. So previous statement, it looks like C is the second fastest because you just started acceleration from that ramp. C, I believe, is the second fastest because it's the second lowest. The lower you are, the faster you're moving, and the order doesn't matter. You could actually have a roller coaster that looks like this, or a roller coaster that looks like this, which I've just made them mirror images. But let's say you start out at 5 meters per second, 5 meters per second. There, that's a little bit more legible, I guess. The speed there should equal the speed there. Those two should be equal. The speed there should equal the speed there. Those two should be equal. Because if you start off at the same velocity and you fall the same amount, I'm kind of assuming that I drew this correctly and both are equally far down, which it looks like I did a not terrible job at that. Then the speed there the speed here should equal the speed here, and the speed here should equal the speed there. irrespective of if it was first or second. So we go huge dip, little dip, a little dip, huge dip, and it should work out to be the same no matter what. It's an interesting principle that I think it's neat that energy doesn't care, and I like that because it means that we can skip over some of that. Makes our questions easier. The other question that I asked was, the other question I asked was, what is the normal force that I experience at the top of the loop? Here's the loop. What's the normal force up there? The normal force at point B up there. The mass, I did end up saying, oh yeah, let's just say it's 350 kilograms. I ended up giving you the answer on one of those slides that velocity at B is 16.1 meters per second. That lets me do this. I know that this is actually not energy. Like this stuff is not going to be energy at all. I just figured, hey, it's a good time to talk about this. It's just a little refresher. It's not energy, but it's stuff that could be on the test. The centripetal acceleration of that cart it's going in a circle. Even if it just makes one complete circle, it went in a circle, or it is in the process of going in the circle. When something is going in a circle, you have to start looking at centripetal things, centripetal accelerations. We know that the centripetal acceleration, so that's the inward acceleration that it's experiencing as it goes in this loop, that is equal to v squared over r. We calculated that. V, we got that in the previous part that was about energy. It was 16.1. Plug that in there. The radius, I believe it was a 12-meter loop, and so the radius is 6 meters. You can look back on the diagram for that, but I believe that the loop was a 12-meter loop, so the radius should be 6. And we can find the centripetal acceleration from that. 16.1 squared over 6, 43.2 meters per second squared. That's kind of a lot. And then we can say, well, if we're dealing with centripetal accelerations, which remember in the book, centripetal acceleration is often changed to radial acceleration because they changed it between versions. So you'll see centripetal versus radial, but it's the exact same thing. So the net centripetal force, I should have written net here to be very, very specific. That is the net centripetal force is equal to the mass of the cart times its centripetal acceleration. Now we just need to figure out what the net centripetal force is. Well, the net force is always all the positive forces minus all the negative forces. But we have to know which direction is positive and which one is negative. Centripetal means center seeking. Centripetal literally means center seeking. So anything that is seeking the center or pointed towards the center, that counts as a positive force. Do we have any forces pointed towards the center? Yes, we do. We've got the normal force and the force of gravity pointing towards the center. The force of gravity always points down, and when you're at the top of a loop, then the force of gravity is pointing towards the center of the loop because, you know, the center of the Earth is even farther down than the center of the circle. The center of the circle is like in the way between the cart and the center of the Earth. So of course, the force of gravity is going to be towards the center of the circle just by coincidence in this case. It's always just down. And then the normal force is down. This annoys people that the normal force is down. It shouldn't, because we talked about how if you've got a ceiling and you push on it like that, well, it's going to push back at you down the other way. You push up and it pushes down on you. So as this thing goes around the loop, we know that the normal force has to be down because anything that you are pushing on, it's going to be pushing on you back the other way. So both normal and gravity are pointing down. And so they're both pointing towards the center of the circle, I should say it that way. And so they both get to be positive. Normal plus force of gravity is equal to the mass, 350 kilograms, times the centripetal acceleration, 43.2 meters per second squared. The force of gravity is just going to be the mass times 9.8, mass times 9.8. And we're solving for the normal force. We plug everything into our calculator and we get 11,690 newtons for the normal force. Question, so then what pushes you upward? Yeah, that's a great question. Imagine, what's a good example? Imagine if Thanos came in and snapped the top of the curve away. Just came in, snap, and as you're going around on this loop, the top half of it just disappears. Let's say that it disappears while you're around here somewhere. If it disappears then your cart is just going to go like fly off this way, like that. It's not going to go in this very quick curve like that. It's going to fly off that way very, very quickly. And that's very different from just going in this very tight circle like that. In order to go in that tight circle, you need to be changing your direction very quickly. Like if you just fly off like that, then you're not changing your direction very quickly. But if you're going around like this, you're having to change your direction very, very quickly as you go around like that, around the circle. Changing your direction quickly means that you have to have a force on you. Effectively, your cart is pushing out on the track. Like as you go around this track, your cart is pushing out on it. If you've ever played one of those build your own roller coaster kinds of games, in some of those games, if you make the cart go too quickly, it can actually rip the loop apart. Like the cart goes around the loop too quickly and it rips the loop apart and it all breaks apart, like it almost explodes outwards. The force is actually from Newton's third law. If the cart is pushing on the track really hard as it's going around, then the track has to be pushing really hard on the cart to prevent the cart from phasing through the track. It's literally the atoms not wanting to go through each other as you go around the circle like that. What pushes you upward? You can think about it as your inertia is like you're going up. As you're going up on this loop, then you don't want to go down instantaneously. Your inertia, your tendency to keep moving the way that you were moving, is really what keeps you going up. But then you have to have that extra force to push you down from the normal force. And so do you stay up this high? No, you very, very quickly have moved over here and you're not as high up. So you don't stay that high up. You move down very, very quickly. These forces are what makes you move down so quickly. And they do so at just the right rate to keep you going in this circle. Yeah, so nothing is pushing you up. You're just failing to go down. That's a very good way of thinking about this because it's just like an orbit. This mathematically is almost indistinguishable from a satellite in orbit. A satellite in orbit is always falling towards the Earth, but it's going fast enough that it never hits the Earth. Mathematically, a roller coaster loop is effectively identical with a satellite in orbit of the Earth, which is also well described by nothing is pushing you up, you're just failing to go down. Yeah, that's a good way of thinking about it.